All right, we're going to talk about absolute analysis today. So far in our study of the motion of mechanisms, we've looked at fixed axis rotation. Now we're going to look at the parts of the mechanism that are both translating and rotating. And as we talked before, both translation and rotation at the same time is called general plane motion. So today we're going to look at the absolute analysis. Now using that, we'll define a point on the body whose position can be described in x and y. Then we're going to find a relationship to the angle of rotation. Then we're going to take time derivatives of that translation, and we're going to find out how they are related to the rotation. So anyway, we're going to try to find x dot, x double dot, or maybe y dot, y double dot, and find out how those are related to omega and alpha. All right, so first we're going to look at something I call sliders. And sliders is where the functional length of a member is changing with time and where there's only one member rotating. And this is a really common kind of mechanism, but here's just an example. Let's say we have a rod that is moving this way through some collar that's fixed, and so it's going in this way and it's sliding against this moving arm that's going in this direction. So you can see that as this moves this way, it's going to push the arm into some rotation pattern here, the rotation about this point. It's obviously defined as some theta. And in this case, we have this length. I call that the functional length of this arm, because this part that's sticking out here doesn't really matter. But anyway, that's changing with time. So we're going to look at that type of a mechanism first. All right, so the first one we'd like to look at here is this. What this gizmo does here is this rod is moving this way through this. These are bearings, if you will, and what we're doing is as we rotate this thing, it moves this piston up and down. The piston is connected to this rod, so that as I move it this way, this piston goes this way, and that shoves the rod DC that way. Okay, so what we're going to do is try to define this in terms of position and theta. All right, so let me just draw a little triangle of what's going on right here, and I'm going to say that this is my position A and this is B. In this case, the length L is fixed, and we have that theta right there. And I guess what we're looking for in this problem is how is this dimension X changing with time? Well, we can find out because the position X means that this whole thing is moving in that direction, which pushes the rod DC that way. So let's find X as a function of theta. We can call that is equal to L cosine of theta. Now that I have my position as a function of theta, it's very easy to take the time derivative. So I'll just say x dot is equal to L. Derivative of the cosine is the minus sign. And we are in the time domain here, so I'm taking the time derivative of a function of theta. So I have to take d theta dt. So I'm going to put theta dot right there at the end. And now I've defined my change in length. I'm going to say that v of CD is equal to x dot, which is equal to minus L sine theta omega. And if I know what omega is, then I can find out what my speed is of that bar. If I want to find out something about acceleration, I take the time derivative again. So I'm going to say x double dot, taking the derivative of this equation, is equal to L. And inside that parenthesis, let's take the minus outside. That way we can put there. So the derivative, we're going to have to use this was the chain rule. Now we have to use the product rule to take the derivative of this, because I got a function of theta and a function of time. So I'm going to say that that's going to be sine theta times theta double dot. That's the first part of my product rule, plus theta dot times the derivative of sine theta. And the derivative of sine is the cosine. But again, cosine is now a function of theta, so I have to have another theta dot. And so I can say that that is equal to minus L sine theta alpha plus cosine theta omega squared. All right? And that's going to be the x double dot, which is the acceleration A of CD. Okay? And in this particular equation, or in this particular problem, it says that it's constant circular motion. So if that's constant circular motion, the omega is constant, which means that alpha would be equal to 0, but that would be what we've got here is the general form that we would use. Okay, let's talk about this guy. This is a little different kind of slider. This one has a collar that's being driven, pulled down by this screw, so it's some sort of a screw mechanism. It turns this way, pulls that collar down. The collar has a pin that's riding in this slot, so as this pulls this down, you can see that theta changes this way. All right, so let's see what our values are. I'm going to change this 18 inches to 1.5 feet because I like dealing in the feet per second, especially since VB was defined here as 0.8 feet per second. So this is VB, and that's equal to 0.8 pulling down. We want to find omega and theta. So let's find out, or omega and alpha. Let's define omega going in that direction. And we need to find a relationship between these distances and that angle theta. Well, why don't we call this distance my y, and we'll do that. And this distance is x down there. So I can say that the tangent of theta is equal to y over x, or tangent of theta is equal to y over 1.5. And 1.5 is a constant now. Now I need to put this into a way that I can take a derivative, but I could, let me put it this way. Y is equal to 1.5 tangent of theta. Now I have what's happening, or what's going on here is y is changing, so this makes sense. If I take the derivative of y, I'll get the change in length here, and I can find also the derivative of theta. So I'll say that y dot, taking the time derivative of that, is going to be equal to 1.5. Now the derivative of tangent, if you look in the resources, you'll find that the derivative of tangent is the secant squared theta. Now again, the derivative of tangent is a function, as a function of theta, is d theta. d theta is this. Then I also have to, because I'm taking the time derivative, I need to also have a theta dot there. Okay, so there's my my equation. Again, this is the chain rule. dy dt is equal to dy d theta. Let me put that d theta dt. We recall that from previous work. That's the chain rule and the time derivative. All right, so now that I have that, I can evaluate that if I want. I'm looking for omega at this spot, so I can say theta dot. Let's see. Let's put this into something we like better. I'm going to say that this is y dot is equal to 1.5. Secant is 1 over the cosine squared theta dot. And so I can say now that theta dot is equal to y dot cosine squared theta over 1.5. Y dot was given here as the change in length down that way, so that's going to be equal to, I think it's called 0.8 over 1.5 cosine squared theta. And evaluating that at 30 degrees, I can see that theta dot is equal to omega, which is equal to 0.4 radians per second. And that was what we were looking for in our first piece of it. We also want to find alpha. So I've got a relationship here for theta dot as omega is equal to theta dot. Evaluating that as 0.533 cosine squared theta. I can now take the derivative of that and find out what alpha is. Now, this cosine squared theta, you may also recognize this as 0.533 cosine theta, the quantity squared. And whatever, there's various ways of approaching taking the derivative of cosine squared, but I like to do it in this way. So I'm going to say that I'm going to take the derivative now again, and so I'm going to say alpha is equal to theta double dot, which is equal to 0.533. And I'm going to use the chain rule on this. So I'm going to bring that 2 over in front, 2 cosine of theta. Now I take the derivative of of the cosine, and that's going to be equal to the minus sine. And that's in the theta domain, so I still need a theta dot on the end of that. And so that's my alpha right there. That's going to be equal to, well, if I evaluate that at, I've already got my theta dot, so if I evaluate that at 30 degrees and omega is equal to 0.4, this theta dot is equal to omega, I can bring that in there, and I can solve this for alpha is equal to negative 0.1725 radians per second squared. Okay, that's how you would solve a little deal like that. All right, let's look at another one. This is a cam, and cams are very common in the absolute analysis, but what we have here is a type of a cam where this cylinder or this round thing here is rotating about a point on its rim. It's being going, it looks like it's going in this direction, so it's being rotated up like that, about this point. And what we want to do is find out the speed or the vertical velocity of this platform. This platform is going to slide on those two rods. There's some bearings or something in there to allow that platform to rise up vertically like that. So as this thing rotates about that point, it's going to push that up there. So let's define our distance y here is equal to, well, it's got a radius here, so there's going to be that r, and then this little piece of the distance here is going to be, that's r right there, so this would be an r sine theta, that little piece right there. So I've got my r is equal to r sine theta. Well, if you recognize what's going on here, as this goes up, it's because y dot is changing, or y is changing. So this y dot is going to be equal to that velocity of the platform. So let's just take the time derivative then. I got y dot is equal to, well, the derivative of r is r being a constant, r is 0. So y dot is going to be r. Derivative of sine is cosine, and I still need my theta dot because of the chain rule. So my velocity, y dot, is equal to the velocity in the up direction. So that's going to be r cosine theta omega is my velocity of this going up. All right, if I also want to know the acceleration, I have to go back to this equation and take another derivative. So I got y dot is equal to that. Take a derivative again, y double dot. Now here I'm going to have to use the product rule. I'll factor out my r, and I'm going to say that that's going to be my u, that's my v. So cosine theta times the derivative of theta dot is theta double dot plus theta dot times the derivative of cosine theta. Cosine theta is a function of theta, so that's going to be equal to the minus sine, and then I have to have another theta dot. And you'll find that most of these derivatives are going to work out like this, where you'll have a theta dot and a theta dot squared, or in this case alpha and an omega squared when you do this product rule derivative. And this again, in this problem, it says that the angular velocity was a constant, which means that alpha is going to be equal to 0. This again would be the general form of the acceleration. In this particular problem, that term goes away, and so this would be r sine theta omega squared. All right, so I want to just refer to several different kinds of mechanisms and several different kinds of approaches that I think might make some sense here. So when you have two sides and a theta changing, like this kind of guy, where this x and this y or this h is changing, the length is fixed. We already solved this problem, but this one is exactly the same. I call this the sine-cosine approach because the height is changing as a function of that theta, and we can usually set up a relationship, well, like we just did. Let's see, I guess we did this one, where x is equal to a cosine. We might have this one where the h is going to be equal to the L sine theta. This one over here looks the same thing. It's rotating. We're trying to find the speed of this. As this rotates this pin slides in this slot and shoves this whole thing up and down. So we're trying to relate the speed up and down to that angle theta. Using the sine-cosine approach makes a good sense there. In cams, sometimes we'll have to be a little more clever. So here's one here where we got a little wheel on top of a sliding rod here, and this is rotating back and forth. So this is probably going to be the driving thing. It's going to be driven in either that direction or that direction, and it's going to cause this arm to move back and forth. But what here we might have to do is find what we're trying to do is find this distance, how this changes, because the change in this distance is going to be the speed, the change in that displacement. So we want to relate that to our omega or our theta dot. So in this case, well, we'll probably have to set up some sort of a relationship like this, where there's a small radius and a larger radius, so that we can say that this triangle is defined, and we'll use the cosine law to define that, such that we want to find a relationship between x and theta, so that I can take the derivative, and we'll do that. We'll say that r2 plus r1 quantity squared is equal to r squared plus x squared minus 2rx cosine of theta. You can see how I set that up. But the cosine law is very helpful sometimes. Here's another kind of a cam where this one's rotating about this point, and what we're looking for is this distance and relating that distance to the angle theta. This one's a little bit easier. All we're trying to do is just say, or what we can say is that this distance r is going to always be there, and what we're looking for here is this little piece of this distance. This distance isn't on the rim, it's out there just some angle or some distance e, so we have x is equal to r plus e cosine theta, and we can take the derivative of that. Alright, here's another little approach here. This slider, these are all sliders because the one we got one dimension is changing with time. So here we have a height here. You can see this hydraulic cylinder is shoving this pin up. The pin is sliding in this slot. As this goes up, the angle changes. So in this case, we got two sides and theta changing. On those other ones, the L was fixed, but in this case, L is changing. In other words, the length, the hypotenuse is changing, and X is fixed. So a tangent approach might make some sense here. We're going to say that H is equal to, tangent theta is h over x, and so h is going to be equal to h tangent theta. Now I can relate this because that's the one I know, or I'm going to try to, I guess in this case I know it, so I can say h dot is equal to x tangent theta, taking the derivative of that using the tangent approach. This is just a little bit different. Here the block is sliding toward this way, and in this case height is fixed, but x is changing, so we have to say x is equal to h cotangent theta. Both of these things you can take the derivative of both sides again and get x dot, take the derivative of this one and get h dot, and you'll have to do the derivative of those tangents and cotangents. They're not very pretty, but they need to be done. All right, and then a couple more here. Here's a window. It's being cranked open, or it's being pushed open by this cylinder here. You can see it's rotating about this one. In this case, two sides are fixed. In these guys, we had two sides changing. This one, two sides are fixed, but the theta is opposite the changing side right here. So what we'll have to do is set this up with a cosine law, similar to what we did over here with this with the cam before. But we can say that this side AB is equal to the square AB squared is equal to 2 squared plus 1 squared, and then we can relate that to that angle right there using the cosine law. And the last one I want to talk about is this little scissor thing. As you can see, what's going on here is this this scissor kind of goes in and out based on the position of this collar up here, A. It's pinned here, so as A goes down this way, it pushes the whole thing out like that. So what we want to do here is define a little triangle like right there, and those are all similar triangles in this sort of thing. They all behave in the same way, but as h changes, in other words, as velocity of A goes down, we can see that x changes, but the length, this L here, is fixed, and so that's related to the angle theta. And I'll say that whereas two sides in theta are moving like this, the Pythagorean theorem might make more sense to set a relationship up. I want to just talk to you about the differences here in this particular thing. If we wanted to relate the height to the theta, we could say that h dot to theta dot is using a cosine. If we wanted to make the x related to the theta, we could relate x dot to theta by using a sine function. However, in this kind of mechanism, we're probably more not interested in how theta is changing, but how is the height and x related to each other. Now, we've still got a trig function, but we'll probably use a tangent kind of thing here so that we could say that the tangent of theta is equal to x over L, or x over h. And so that we can set up our x relationship like that. And then when we take, but this is a little hairy to do the derivative, because we have to do this secant squared, and then it's also all three of these variables are changing, so we have to use the product rule here and do that. And when we get done with it, we have a derivative function. We have an x dot and we have a theta dot and we have an but it's not really a good approach because all three of those things are changing. So in those cases, it might be better to relate x and h through a Pythagorean theorem and say that L squared is equal to x squared plus a squared, because this is a right triangle like that. And now we can more easily take the derivative of something like that, where taking h on one side and x on the other side, the derivative of L being a constant goes away, and we can get a relationship between h dot and x dot through the angle. Now we can say that for any angle of theta, we can define what x dot and h dot are. So anyway, this might be a better approach for doing something like that, where we're more interested in how the height and the x distance are related to each other than our interest in the angle.